Okay. In the last example, we talked about VSEPR theory of two electron clouds. So they say it is linear. But let's talk about those ones that have three electron clouds. Okay. Again, the first step, if you remember from the previous video, the first step is to write or draw the dot structure. Okay, a dot structure is also called level structure. So that's the first thing we have to do. So let's do that very fast. We have three valence electrons there. We have 1 times 3, which is also 3. 3 plus 3 will give me 6 valence electrons. So between aluminum and hydrogen, aluminum is obviously the central atom. So because hydrogen can never be the central atom, I explained that already. Okay, so we have that. So for 3 hydrogen atoms we have around. So every bond here has 2 electrons. So 2, 2, 2, that's 6. 6 minus 6 will give me 0. So this is the structure of the level structure of aluminium. This is the level structure of AlH3. You want to say that aluminium does not have 8 electrons around it. Yes, aluminium is one of the exemptions of the architecture. The second rule is to count the number of electron clouds. So let's count electron cloud around the central atom. So there are electrons here, so this is electron cloud. Electrons here, electron cloud. Electrons here as well, electron cloud. And so now we have 3 electron clouds. The 3 electron clouds. So the next step now is to predict the electron cloud geometry. Predict the electron cloud geometry. If you look at this now, we actually call this trigonal planar. Reason being that if you look at this, this can fit into a plane. So imagine I have a plane shape like a rectangle or square or something. Let's say this red dot here is aluminium and the orange dots are the hydrogen atoms. Okay, so we have this, something like this. So it fits into a kind of plane. So that's just a way to think about it. So we say that this electron cloud geometry is trigonal planar. It makes sense. Trigonal planar. Trigonal from the idea that there are 3 terminal atoms here, and planar, you can fit into a kind of plane. It's kind of plane. So, and the bond angle, if you look at this now, you can see that the thing about VSEPR is that the electron clouds try to stay very far away from each other to reduce repulsion. They don't, right now, if you bring 2 electrons together, if this was closer together, it would be a great repulsion because negative charges, what they do, they repel each other. There will be minimal repulsion as possible. You have to base yourself at a kind of angle that the repulsion won't be as great as that. That's why you see here that the electron clouds, as this one, this, and this, they are like at equal distance from each other. Do you get? So the angle here, and the angle here are kind of equal in a way. So if I say, let's say everything is x, for example, so we say x plus x plus x, since this is planar, if it's a kind of 2D structure or something, it's kind of 2D. So this will give me 360 angle at a point. I'll be 3x equals to 360. So x is 120 degrees. So this is just a mistake about it. So the bond angle here for a trigonal planar geometry is 120 degrees. So this is the electron cloud geometry. And the last step now says you should ignore the lone pair on central atom. So if you look at central atom, there's no lone pair on central atom. So there's nothing to ignore. That means that the geometry of AlH3 is also what? Trigonal planar with a bond angle of 120 degrees. Let's look at BF3. Again, the first step is to draw the level structure. So boron has 3 valence electrons and fluorine has 7 times 3, that's 21. 21 plus 3 will give me a total of 24 valence electrons. So boron here will be the central, has a lesser electronegativity, and we have our 3 fluorine atoms around the central boron. Okay, we have used 1, 2, 3, that's 6 electrons. So subtract this from here, we have 18 valence electrons. So what do you do now? We assign the valence electrons to the terminal atoms. So let's assign that, assign. We have to complete their octet configuration. So that's done. So we assign 6 per fluorine times 3, that will give me 18. 18 as 18 will give me 0. So hence this is the structure of BF. Again, look at boron. Boron has only 6 electrons around it. Yes, others is around it. So boron is also one of the exemptions of the octet rule. You understand? So now that we have drawn the Lewis structure, the next thing we have to do now is to count the what does it say? Count the electron clouds. So let's count the electron clouds around the central atom. So there's the electrons here, so that's 1. The electrons here, that's 2. And electrons here, that's 3. So here again, we have 3 electron clouds. So that means that the electron cloud geometry is trigonal planar, since you can fit it to a plane again, as I explained earlier. Trigonal planar. And what will be the bond angle? Take a second to pause the video and tell me what the bond angle will be. Okay, the bond angle here, since I told you that electron clouds, they stay in a way that they try to reduce repulsion as possible. So the electron clouds will be at equal distance from each other. So to be at 120 degrees here. So the bond angle for this molecule is 120 degrees. The last step says you should ignore the lone pairs. Is there any lone pair on boron? No lone pair. So hence, the geometry of the molecule is trigonal planar. So I don't want you to confuse electron cloud geometry and geometry of the molecule. They're quite different. So you have to ignore the lone pairs on the electron cloud on the central atom to get the geometry of the molecule. Okay, lastly, we have SO2. So let's quickly wrap up on this. We have SO2. Again, let's just the level structure. S is 6 valence electrons. Oxygen is also 6 valence electrons times 2. That will give me 12. 12 plus 6 will give me 18 valence electrons. Okay. So what will be my central atom? We should look at your periodic table. We have oxygen up and we have sulfur beneath it. Okay, I told you guys that electronegativity decreases. It decreases this way, which means that oxygen will have a higher electronegativity than sulfur. So sulfur will have a lower. So hence sulfur will be the central atom. So we have sulfur and we have our oxygen like this. Okay, so we have oxygen atoms attached to the central sulfur atom. Okay, so we have 2, that's 4 electrons. Move 4 electrons from here. We have 14 valence electrons. Assign them to the terminal atoms to complete their octets. Assign. So what do we have now? We have 1, 2, 3, 4, 5, 6. We've used up 6 times 2. We've used up 12 valence electrons. So how many is left? We have 2 valence electrons left. So what do we do now? I don't know if you remember, we are going to assign that to the central atom. Okay, so that is complete. 2 minus 2 will give me 0. So this is the Lewis structure of the compound of SO2. But if you look at this now, sulfur here has just 1, 2, 3, 4. Okay, let's count again. 1, 2, 3, 4, 5, 6. Yes, 6. It's now up to 8. So what will sulfur do? Again, as I explained in the previous examples, I said sulfur here will pick up one of the lone pairs of oxygen to form an extra bond. Okay, so this will become, we have our O, we have our S, we have our O. This oxygen here we still have its 3 lone pairs of electrons. But this one over here, we have just 2 lone pairs of electrons because it has used one of the lone pairs to form a bond with sulfur. So you can see now sulfur now has a stable octet configuration. But it can happen the other way around, where sulfur can decide to take a bond from here, a lone pair from here instead of taking from here. So what will now be formed in that case? Something like this, just a little sketch. Something like this now as 2 lone pairs will now be a double bond here instead of being a double bond here. Do you understand? So we call these things resonance structures. I will explain that later. Okay. So the next step says you count the number of electron clouds around center atom. Let's count. Are there electrons here? Yes. Electron cloud. Are there electrons here? Yes. Electron cloud. Now, what about this lone pair? Are these electrons? Yes. So this is also going to form another electron cloud. So we have how many electron clouds we have? We have 1, we have 2, we have 3. It means that the electron cloud geometry, just let me write ECG. I can start spelling that out. Let's take our time. Electron cloud geometry of SO2 is also what? It's also trigonal planar. This is the electron cloud geometry. This is the electron cloud geometry of SO2. Okay, normally the bond angle for trigonal planar, the bond angle should be 120 degrees, right? 120 degrees. That should be the bond angle. And there's something here. The electron clouds that are formed by lone pairs. Look at this electron cloud, this one in red over here. What formed this electron cloud? It is the lone pairs in orange, right? These lone pairs that form the electron clouds. Now, the electron clouds formed by lone pairs, note that they show a greater repulsive force. That means that they tend to push away other electron clouds more. That means that this one in red, this electron cloud formed by this lone pair, will push, let me rub this off so this will be very clear, will push these other electron clouds away. Will push them, like kind of bend the angle. Now the angle here was normally 120, right? So it will kind of like bend them more, because I told you already that electron clouds formed by lone pairs have a greater repulsive force. So to bend them more, just by reducing this angle to something approximately 119 degrees, around 118, 117, 119 degrees. So that means the bond angle of SO2 now is not actually 120 like these other examples, but approximately 119 degrees. So now the last step says, for us to really number the shape of the molecule, we ignore the lone pair. So let's do that. Ignore the lone pair. If I ignore this lone pair, that means I ignore this electron cloud here. What do I have? It looks something like this, where we have sulfur here, and we have oxygen here, oxygen here. This looks like a V. Turn it upside down. Turn it upside down, it looks like a V. Where we have our sulfur, I just inverted the image like a V. So we say that the geometry of this molecule is V-shaped. That is a V-shaped geometry, or we say it is bent. So SO2 has a V-shaped geometry or a bent geometry. This is the geometry of the molecule itself, not the electron cloud.